So, good morning everyone. In today's class, we are going to learn about basics of quantum computing, then quantum machine learning, and then second classes we will learn about this quantum security, specifically the post-quantum cryptography and all. So,
Good morning, welcome to the last day, last show. So, first we are going to talk about quantum machine learning or quantum AI, and then we talk about quantum security, and throughout the discussion we will talk about how AI can solve the security problem in the quantum domain. In the last 9 days, we basically talked about AI and security in the classical domain. Today, we are going to focus on quantum domain. So, what I am going to do, I will introduce quantum computing a little bit, and then we will straight go to the quantum AI and some of the steps that are important in quantum computing, so that you can relate to classical domain, how is it similar or how is it different. So, if you look at quantum computers implemented by different companies, they are using different technology, and the classical computing technology is based on electrical properties 1 or 0, high voltage or low voltage, but this does not follow your classical properties, rather it is basically follow the quantum physics or quantum dynamics. And although it is not shown here, in a month or so time frame, Microsoft came up with the topological quantum computer. That is not classical, that is not quantum, that is some magical phenomena. Those of you want to learn about. So, I am going to talk about qubits, which is the quantum phenomena. This is about anion. So, they are known as anion. If you are interested, they actually build a machine where they can capture that magic and do that reliable computing using topological quantum computers. So, what I want to highlight something. So, throughout this I am basically going to talk about the differences between classical, so that you can relate to it. So, in classical, earlier people are putting 1 or 2 transistors in 1951, now we are putting billions, and transistors are getting smaller and smaller. These days we are fabricating with 3 nanometer. So, it is that thin. Here actually, if you think the analogy of a transistor, which is qubit, they are getting bigger and bigger and bigger. More we try to put in, instead of making them smaller, they are getting bigger. The reason they are getting bigger, as of today, this is how quantum computers look. So, actual quantum computer is really tiny, what we call as quantum computer. So, think of a finger, in a tiny finger you have that chip, that is the quantum computer as far as we are concerned. But for the rest of the world who do not know anything, for them to sell something in $100 million, you have to show something, right. This is what we show. And basically it has a lot of wires, and that chip, tiny chip is sitting inside, and all these wires are connected from the quantum computer to all the way to all these devices you see. Those are all classical computer, FPGA and all that stuff. This is actually your quantum computer, although deep inside a tiny chip, that is actually where it is fabricated, and they are going to exploit the quantum phenomena, dynamic physics of the phenomena. It is not the electrical property, it is not the electron flow, then it lost the quantum property, then it would behave like a classical computer. So, normal understanding in the regular world or normal people, quantum is very fast, that is not true. It is just that quantum computer can solve certain class of problems theoretically significantly faster than classical computer. You have seen one of them, or at least heard one of them, like prime factoring. But if you want to do your addition, if you are thinking I want to do my addition faster than quantum compute, classical I can do addition in whatever 1 nanosecond, quantum I will do in no time, 1 picosecond, that is not going to happen. In fact, we do not actually know how to do addition in quantum computer. If you do it, you have to do it thousands of times, you have to measure and you have to hope and pray, maybe once the result would be correct. So, just make sure I dispel that idea. So, I talked about actual quantum computer is really tiny, a chip, but everything around it like supercooling, absolutely supercooling temperature you need, and you need all these classical computer to sit there, connect and to make it work. Now, this is basically the way to visualize the quantum phenomena, although Feynman said do not try explaining any quantum phenomena using any classical example, because that would be 100% wrong, because there is no classical analogy. But today I will try that, and full disclaimer, any comparison I make, they are actually wrong. It is just that it makes you kind of feel and understand, instead of showing you lot of equation. I will try not to do any equations at all. So, a cat, this is the Schrodinger's cat, and Schrodinger is kind of assumed as the godfather of this domain. So, Schrodinger basically saying you put a cat inside the box and keep some poison, and that is kind of closed, and then it is intelligently closed. If cat is intelligent, it will be able to open, and if it opens, most likely it is going to drink or spill and going to die. Now, if cat's owner is outside and you ask the cat's owner, did your cat, is your cat dead or alive, that is actually the qubit. You can't say it, because if you are the cat's owner, you are going to think my cat is intelligent. If your cat is intelligent, it is going to be able to spill and drink and die. You do not want your cat to die. So, therefore, you are not going to say that. On the other hand, you can't say my cat is really dumb. I do not think it would be able to open that phenomena. And so this basic idea that when box is closed and soundproof, the ability to tell that whether the cat is alive or dead is not possible. So, then it is probably alive and dead at the same time, 0 and 1 at the same time. That is the analogy of a qubit. A particular computing node in quantum dynamics, a particular thing that is both 0 and 1 at the same time. And little history, and that is what I think I can safely say that nobody understands quantum mechanics. That is the Feynman, and he is assumed to be somebody who can took all the theories and equations that Schrodinger came up with and actually implemented and showed it work, exactly the way Microsoft took 17 years to actually show topological quantum phenomena. It is all nice thing, all these magical things, when they come, either they self destruct or they start dancing, they actually form such a formation, and that actually can be implemented on real device, can be fabricated, and you can measure those, control those. That took 17 years and hundreds of millions of dollars of funding. Anyway, I am going to skip all of that, and what I am going to talk about now, what is the intuition? So, I prepared this intuition for anybody to understand, even somebody from elementary school, but I am going to ask a question. So, you have to understand. So, when you are in a rocket and the rocket has a position and a velocity, right, and remember I am taking analogy, those are all wrong. When you have a noise cancelling headphone like Bose headphone, it has a noise cancelling phenomena. How many of you know how noise cancelling works? One hand. So, when you have normal waveforms, normal signals, you have to identify those signals and frequency, and then you have to create signals which is exactly opposite, and then they will cancel each other, right. So, but you have to identify which one is noise. In childhood, when I used to go to the field and doing what they call it, removal of weeds, I had real confusion. The weed and the actual rice plant look exactly the same. I asked my dad, which one should I remove? He said, look at the distribution, which one is more, that is the rice, whichever one is less, that is the weed. It coincidentally that weed is actually rice, it is just that it got mingled. Unlike these days, you go to government shop, they give you a sealed container of the seeds, they are completely refined. Those days it is like everything get mixed. So, it is really one of the rice you call as a weed, another rice you call. So, the biggest problem in noise cancelling is actually identifying which signals are legitimate voice and which signals are noise. So, Amar Bose from MIT was able to do that. Now, if you put this headset on the airplane, that is actually a quantum computer headset on an airplane or the rocket. Assume rocket as a human being, this amount of noise is too much, that is quantum computer. And the key idea here is a quantum computer has a state which can be controlled, and the coefficient states are complex number that can constructively or deconstructively interfere. Remember that noise signal cancels each other. Now, what is happening over the years? The computers we have today we call is noisy intermediate scale computing. Everything is really noisy, and in a moment I will explain why are they so noisy. That is why the computing today is not reliable. So, 2023 IBM let me try writing exactly same way. 2023 IBM came up with something like 1023 or some number, about 1000 qubit gate. So, that is basically what we have today, and these are kind of noisy. When I talk about quantum error correction, I will revisit it. To make a qubit reliable, you need 4 of them to guard it, 4 or 5 together becomes a logical qubit. If you take any number 127 divided by 5, you are really left with around 20 qubits. With that qubit you can't compute much, but going forward when you have computers with lot of qubits, we will be able to do reliable computing exactly the way you do in classical. We never think of alpha particle heating and all that stuff, we never worry about it, and that is the problem. But the problem with the classical and quantum is this is a age old puzzle. Even classical domain, because even the day I was doing PhD, it is 18 micron technology. Now we are talking about 3 nanometer technology. It is already going or seeing the phenomena of quantum dynamics. They are already facing some of these noise and unreliability, all these problems, but very soon it is going to get into the realm of quantum. That is what people are saying. For when it entered the nano regime, people are saying, oh, now it is not going to work, but it is still working, reliably working. When you run a program, you do not worry about it, right. So, quantum computers, when they reach that stage, nobody will talk about it anymore. You will write quantum algorithm, which I will show in a moment. You will run computers, and any questions so far? Now, today even with the quantum kind of story or the unreliability or noisy story, people are still able to solve certain class of problem. Today's lecture I will focus on quantum machine learning. Certain class of problem, quantum communication is very stable and it relies on the idea of entanglement, and we believe in that philosophy in India. Mother and kid has some entanglement. If kid is sick, mother will feel some pain in the chest and all that stuff. Whether that is true or scientifically not, or we do not know, but in quantum domain it is true. You can take 2 qubits, make it entangled, keep one in India, take another to Australia. If you measure, do anything, observe anything on the 1 qubit, you exactly know what is happening to other qubit. Real life, bad analogy. If one of my shoe is right here and it is left, it does not matter where my other shoe is, you actually know that one is a right foot shoe. So, that is kind of the issue of entanglement. How do we create? I will talk about it, but the thing is, in communication, once you entangle and do certain transformation to this qubit, then the information you already get from the other one. And in fact, this is also known as the whole Einstein, Schrodinger, all that paradox. How can something move faster than light? It will take me a semester to explain that phenomena, but just to tell you, it actually does in this particular context. Theoretically, you can leave that qubit from here to, let us say, Saturn, and you make certain changes here, you are guaranteed that same change will happen there, but let us not get in there. Quantum communication is actually used, at least based on published result. Chinese president uses quantum communication when talking to security people, security apparatus. Quantum sensing is another one. It is basically sensors that do quantum sensing. It has all its advantages. Quantum machine learning, I will zoom in, you will know anyway. In the future, the sky is the limit, because everything is reliable, you can do all that stuff, and it would build on top of quantum error correction. I will talk about little bit of quantum error correction today. Any questions on this space, where we are, what we expect, and what is going to happen? So, head to head comparison. When you talk about today in classical domain, it is either on, or switch off. So, that basically is your 0 and 1. In quantum domain, they are 0 and 1 at the same time. Remember Schrodinger's cat analogy? Same time. That means, if you think of a qubit as a tiny dot and you try to measure, you are not going to get, first of all, measuring collapses it, that is a different problem. If you want to know what it is with some probability of 0, it is not written as 0, it is written this way, and some probability of 1, both at the same time. But what is nice property, because we can do alpha square plus beta square equal to 1. Now, it is theoretically possible, at some extreme it is only 0, alpha is 100%, beta is 0, and some probability it could be 1 extreme, but that is like 2 points in an infinite space, you can't just guarantee it. You can try transform, we will talk about it, but and this gives it the power. So, let us observe this phenomena. This is basically every qubit. How we do it, we will talk about it through pulses, but it is both at 0 and 1 at the same time with some composition of them. So, that is basically about the qubits, and then in terms of computing ability. So, this power is not the power, computing power. In classical, you put more transistors, it linearly increases. You have one ALU, whatever is the performance, you put 2 ALU or 2 processor, double the performance. Of course, it assumes your program has parallelism, compiler is able to generate parallel thread, you are able to keep those processors busy, all of that is important, but theoretically you can have linear increase. In quantum, it is basically exponential increase. Can you tell me why it is exponential? What did I tell today already that explains you it is in exponential computing ability? Error handling actually is a problem, I will come that later, but why it is exponential? Because recall each of them. So, because of two reasons, each of them is in 0 and 1 state, that is known as superposition. I will take a incorrect classical analogy, but entangle. So, superposition and this whole story of two people can be entangled, that is the entanglement. These two essentially makes quantum computer so powerful theoretically. Today they are not reliable, that is why you have a problem. Theoretically they makes them powerful, but here is a incorrect classical analogy, because everybody is talking to everybody. So, then if there are n qubits, you have factorial n ways of. So, really you have 2 to the power n potential computing ability. So, in quantum domain it is a order of 2 to the power n computing ability, in classical domain it is a order of n computing ability. N transistors, n ALUs, max parallelism of order of n. Here n qubits, because theoretically everybody can talk to everybody. Now, actually they do talk, everybody is talking to everybody, and that actually causes the problem, which is the noise problem. Because if you think about it, if all of you guys are talking to each other and I am also teaching, nobody will listen anything, but here objective is final, whatever is the objective we are trying to achieve, can you achieve that objective? Let us say I said, okay, you guys get together in a group, discuss this and come up with a solution, or whatever you think. Do you want to have a class after the lunch, or you do not want to have a class? If you guys keep talking to each other, nobody will reach any consensus, final objective is not done, right. But this idea of, so one power is entanglement, everybody can talk to everybody. It is a superposition, you may not realize it is actually super powerful. Somebody is 0 or 1. Here you are saying somebody could be in infinite possible scenarios at the same time. So, the potential state space is huge. So, computing in that space, here to create a state space you have to create a graph of n nodes, n square node, then you are representing. This one naturally represents all these huge state spaces, all these problems. So, it is like a huge FPGA fabric where you can compute anything, and they can all run in parallel. So, that is basically computing ability, and that is actually the danger too. If you tell anybody that I told them classical computer noise is not an issue, they will kill me, because that is their bread and butter for most of them. Basically the people work in the back end in layout, fabrication or post manufacturing, all that reliability issue, and but in quantum it is just too much more, a lot more. So, if you look at the quantum noise, this is nothing. Here you compute once, when do you have to run your same program twice or 3 times? Never, right. Here you really have to run 100 or thousands of times same program, and then you kind of figure out what is the result, because every time it is producing wrong result, at least today. Now, when people say, and which I am going to say, forgive me for saying that quantum machine learning is really interesting and exciting, but what I am not telling you, to use quantum machine learning I have to take classical data, convert into quantum form, that will take a lot of effort. I have to run same computation million, if not million, thousand or hundreds of times, that is taking time. Then I am saying, oh, I am 1000 times faster, right. That is not a great idea. because I am not talking about how much time it take me to do classical to quantum conversion, I am not talking about how many times I am running, I am simply saying one run how faster it is, right. So, there are all these things when people tell you something, take with a pinch of salt, then things should be fine. The final one is the thing I talked about, that do not try applying quantum computer on anything, on everything that you want to do. I will give you a flavor on what type of problems you should apply, and if you study the theory of computing or quantum computing, there is a quantum polynomial time, a class of problem. Earlier if you studied quantum computer computing complexity earlier, it will not there, but these days you will find another class of problem, quantum polynomial time problem. It is kind of a class of problem. For those problem, quantum computer is wonderful, certain optimizations. Let me take a specific example. Let us say a biology or chemistry company developing an anti-aging cream. For them to do the experiment, they take the particle, and those particle then they do different experiments and try to figure out whether that would do, if you put it on your skin, would it make you 10 years younger or 20 years younger, right. Now, doing those experiments, those chemical reactions, if you want to do truthfully, it is going to take the age of the universe. So, in classical computer what people do is actually joke, take the thing, put it on a beaker and put the litmus, if it is green it is great, if it is red it is not good. Like what? We should put on somebody's skin. They are like no, we need this approval, that approval, then we need to find a third world country where people have no rights, then we send them there, and 10 years 20 years we will do. First we do on the experiment, then we do on mouses and guinea pigs, then we will find a third world country, and after that FDA will approve, then it will come on the market. That is why they charge so much premium. Anyway, so here in quantum computer you do not need any of that, you can completely do computation. If you can model skin correct way, if you can model those atomic particle and their reactions, you can accurately compute. Then what is not going to happen, that well it on experiment it looks fine, but when you put on somebody's skin it just it develop rashes, it will not going to happen. Those optimization problem, analysis, simulations, these do amazingly well. That is why people in chemistry, biology, those simulations, they are the biggest user of quantum computer. In fact, one of the diagram here is incorrect. There is a class of quantum computer, a company called D-Wave. They are building quantum computer of these qubits, but they are not general purpose quantum computer. They are annealing type of quantum computer. The applications that you need simulated annealing or annealing, those quantum computer will do well, and the chemistry, biology, all these people are using the D-Wave kind of quantum computer. Now, if you are a classical designer, then you kind of know how the gates are, what the truth table. In quantum domain people do the same thing. It is just that the gates are, this is Hadamard gate, this is kind of entanglement, and this is the input, zeros and ones, this is the expected output, and there is a notion of truth table, we call it unitary matrix. But the key point is, if you can see all the numbers look same except there is a imaginary or complex number, that is actually the constructive or destructive interference. So, if you are a classical engineer or quantum engineer, that is basically not much of a difference. And in fact, you do not, if you can call yourself quantum expert if you do just two things. IBM Qiskit, there is a simulator, you can play with it, it comes with a tutorial, and all you have to do know is linear algebra. At the end of the day, if you abstract it out right, it is all about matrix manipulations, then you can call yourself you are the quantum expert. Now, let me introduce the algorithm first, because that is the starting point, and of course, we briefly talked about source factoring algorithm, that if you have two prime number multiplied, can you factor it in a very quickly. There is a Grover search algorithm, instead of taking order of n time in an unsorted set, it will take square root of n time, but I am not going to talk about any of them. I am going to talk about one algorithm I developed, not because I developed it, because I want to take you through the steps we took when we did not know anything to coming up with that algorithm. Those algorithms are not famous, but that will give you two ideas. If you want to develop a quantum algorithm, what steps you will take and what is this catch, because if you do not know what is quantum polynomial time class of problems, which problem you should try to map to quantum, you will get that idea. And why is it faster? I will give you all the insight, let me walk you through. So, this one is basically a clustering problem, and clustering is needed in everywhere. I do not waste time, I do not have any of these account, Facebook and whatever, in Instagram, whatever crap it is, but even if I do not like, rest of the world does, and when people decide whom to give how much money and all that, who is influencer, right, it all depends on how many people connected to it. So, then identifying these clusters is important in social networks. It is also important in many other domain, even when they are doing brain MRI and trying to figure out is it cancerous or not, they try to find out different kind of protein and whatever composition, that is also clustering problem. Even when Google, you search something in Google and they come up with some list, they also do some kind of page ranking algorithm, that is also based on some clustering. So, given a graph, how do we figure out cluster is a problem that is used everywhere, we looked at it, and the best possible algorithm that was there is spectral clustering. I will not get into what spectral clustering so much, other to say once you have a graph, you do a spectral analysis using the same term to define it, and once you spectral analysis, it gives you bunch of values, either values are here or values are here. It is kind of a simple kind of clustering algorithm in machine learning, that is the spectral clustering. But if you do spectral clustering in your classical computer, it is going to take order of n cube time, where n is the number of nodes in the graph, not even n square, n cube. But if you do in a quantum computer, it is in order of n time. I am going to tell you what is the catch, what is quantum computer doing exactly to reduce from n cube to n. Let me try to show that. How many of you recognize this diagram? This is from your 10+2 book. What does this diagram shows? Yeah, that would do. So, those of you do not recognize it, I do not know whether you opened the book or whether your teacher opened the book when the teacher was studying in their 10+2. But anyway, so this is basically showing that for hydrogen wave function, which roughly speaking, if you recall, every atom has something in the nucleus, electrons rotating around, some are loose, some are tight, there are a lot of orbits, some of them do not like their orbit, they always like the other orbit, they want to move, all this stuff going on, it creates magnetic field, and that magnetic field you can represent, and this specific radius, angular momentum, projection, this is known as eigenvector or wave function. If we can control any of these two wave functions, we have a qubit, that is the quantum dynamics. Physics, you take the physics and you implement in quantum computing, that is a qubit. You put lot of qubits, that is your quantum computer. We will talk about how to program them. So, of course, nobody uses hydrogen because controlling this one is actually hard. Microsoft is doing something else, IBM is doing superconducting qubits, some people are doing trapped ion, different people are doing different thing, but that is the key idea. Now, when we looked at it, we kind of figured out that there are 4 stages in basically spectral clustering. One of the stages that take most of the time is computing eigenvalues. So, we wanted to do that. This is the circuit we had to design. When you talk about compilation, it will make more sense. I wanted to show you, if you want to do in a classical computer, how much you have to compute, a lot, and most important part I want to show you, this summation, e to the power and all that stuff is computing eigenvalue in a classical computer. In a quantum computer, you program a qubit, measure it, you get the eigenvalue. You do not have to do all these hundreds or thousands of instructions in a processor, you just set it right, initialize it, read it, done. Why? Because quantum, the computers or these qubits and all that, their natural phenomena is they are eigenvalue by themselves. What all these formation, all these magnetic field, so then that is basically this stuff is essentially they are doing eigenvalue computation. So, that means if you can initialize them right and get the picture, you actually got the eigenvalue, you do not need all these thousands or million lines of instruction. Now, if you want to design another quantum algorithm, see if eigenvalue computation is a core kernel part of it. If eigenvalue computation, which is common part in many analog design and optimization problems, then quantum computing is a perfect fit. Is that the only way to do it? No. I just wanted to walk you through how we realized, oh, eigenvalue computation, that can be done naturally here. We have to set the parameters right, it would orient itself, then you take the orientation, that is the eigenvalue. And if I finish this, you will see what it is we are trying to do. So, we are basically doing eigenvalue computation, and those values we are plotting, and either they are in this cluster or in that cluster. So, we still have the initially the graph, you get the matrix, but this computing eigenvalues. So, this eigenvector projection is extra step we have to do, because remember, or I will tell you, you can't measure a qubit. If you, so for example, we have a kid and kid is making lot of noise, but then if you wanted the kid to do something and hold the hand, they are like the most innocent one. Those of you know cats, they always do that. They are the naughtiest one, and then when you come home and they are like the way you are saying, you can't say anything. When you touch any qubit, it would collapse to 0 state. You do not get anything out of it, but it was always noisy, completely 0 and 1 all the time. So, that is basically the algorithm. Any questions? Now, we are going to do the quantum machine learning. So, I am going to solve one specific problem, but before I do that, I want to show you this whole classical and quantum. Classical is one word, quantum is one word. So, there are 4 possible combinations. You are doing classical data and classical computer, you are doing quantum data classical, classical data quantum, and quantum data on quantum computing. Where the data comes from, what type of data it is, who is the computer, 4 possible combinations. And in today's world, when we say quantum machine learning, these 2 categories are kind of treated as quantum machine learning, because this one we are taking quantum data, but still running on classical computer. So, this is not considered anything quantum, just data happens to be from quantum, who cares, right? It is some data, whether it coming from neural network or biological network or quantum computer, you are still doing classical computing, but here computing is quantum, either on classical data or on quantum data. That is known as quantum machine learning. Why is it called quantum machine learning? Wait for few more minutes. So, the way people use today in the world, unreliable world of quantum computer, is something called, people use variational quantum algorithm. The way you want to visualize, you have an algorithm, but there are some parameters that you can tune. If you have a sorting algorithm, think about it again, incorrect classical analogy, think about the in bubble sort, you have 2 loops and the loop bound you can change, but it does not make sense, because the number of things you are trying to sort, loop bound is fixed to that. Let us say it is not fixed for whatever reason, or number of iterations, it is not 2 for loop, let us say you can do n for loops. Some parameters are there that you can tune, and that is guaranteed to improve the performance, and such a algorithm are used in all over the place. I will show example in error correction and compilation, but it is used everywhere, from physics to math to even the machine learning itself. It can use variational quantum algorithm with wide applicability, error tolerance, scalability. So, the way people use today, in a quantum computer you want to compute something, it could be the computing eigenvalues I just said, and then after few seconds, after few iteration, after one shot, you want to read it and give it to the classical computer to see, am I doing right, am I going in the right direction, do I need to change my trajectory. Classical computer will give the feedback, and those parameter, think of these are adder, subtractor, whatever they want to visualize, that is actually not true, then those can be parameterized. So, parameter values will change, it will do computation again, you again look at the trajectory. Ideally you want to converge in 1 or 2 iteration. Although it is called quantum machine learning, actual machine learning is running on the quantum computer, sorry, classical computer. Quantum computer is doing the computation of whatever algorithm you are asking it to compute, let us say spectral clustering or whatever it is, classical computer is doing the machine learning. Now, inverse problem exists, that is not popular, people are still publishing because they do not know what they are doing. Remember Feynman said, it is not my statement. So, what they are doing is they are taking machine learning algorithm and saying machine learning is slow, let me use some of the machine learning problems and map it to a quantum computer, let us quantum computer speed the machine learning. Quantum computer cannot reliably even add, subtract, multiply, nothing. What computation will you map? People are mapping, people are publishing, they are getting best paper award. try not to publish those things. Now, are they useless? We do not know. Maybe many years later when quantum computer would become stable, maybe those problems all would become relevant, all those publications would be great. If this does not become stable, all those are useless. But this one is useful, everybody using it. Do the quantum computer, but the one catch, did anybody find a flaw in this mechanism? Yes, please. Bottleneck of the classical. Very reason we want to start with quantum computer, it is exponentially faster, right. Even the quantum polynomial class of problems. Now, we are slowing it down by the classical computer, not just one, we might have to do multiple iterations. So, but at least for the time being in a noisy quantum regime, this is what is the state of the art. Yes, please.
One question, sir, just to understand this better, these parameters which we use, the weights and biases, is that what the quantum computer is giving back to the classical one?
No. So, this has 4 qubits, right. Oh, one thing I forgot to mention, I should have said, quantum computer is more like FPGA than like a processor. Why do I say FPGA? Literally the way you are seeing it looks like this way, but really this quantum computer all it has is 4 qubits somewhere, that is it, that is all it has. We send electrical pulses which we will show in a moment, then they start dancing in a manner, talk to each other, do not talk to each other. I am forming a gate to say, oh, Hadamard gate, oh, you guys are married from now on, then I apply another gate, now you guys are divorced. So, we are doing this dancing game by sending pulses, and those things start behaving like a different gate. This is basically same qubits in time step 0. This could be same qubit in next time step or the 2 qubits later, again they are single. We are measuring each of the qubit at the end of the computation. All you have 4 qubits, that is all your computer in this example. You could have 8, 10, 15, but in this example we are only using 4 qubits. It is more like a reconfigurable computer. You have reconfigurable fabric, you can make them behave in such a way, and you over a time frame you send some pulse, they behave such a way, send another pulse, they transform into something, and so on and so forth. It is over a time, this is what is happening to the same 4 qubits. They are transforming themselves into certain behavior. Any questions?
What is the input to the classical computer?
Oh, you had 4 qubits, you measure those 4 qubits, give those measurement values. Yes, please.
What is a qubit?
A qubit is something like remember in classical we had switch on and off. Here instead of on and off, it is both on and off, partially on, partially off. How much on, how much off, that is basically kind of a qubit here. So, if you think carefully, become little silly, then actually what we just talked is basically a state preparation problem. Let us say you want to do a sorting of 10 numbers. You put bunch of number in your register, run the sorting algorithm, the sorted result in your register. It would be nice if I can initialize those registers with the sorted value. I know it sounds silly, if it was sorted, why am I running sorting algorithm in the first place, but really this is a state preparation problem. And that is what I wanted to show you, that if I know the end result, I just prepare the state, and in quantum computer you can actually do. And I will we developed a very interesting idea for that, I will talk to you in a moment. But essentially, although final result I am not talking about, I am talking about when this machine learning tool figured out something, how parameter need to be initialized, think of those values are coming, you are initializing those parameters or those registers, that is basically the state preparation problem. And then you measure, and those measurement you give it to the classical computer. Any questions? So, most people work, when they say quantum computing, they are working here. 2 other problem, most people do not work, then who works those areas? That is me. State preparation and quantum measurement, and both are important. I will try to give you that flavor. Do not get into the crowded territory where people are working, try to work on the areas where people are not working. All 3 of them are important. If you do not prepare the state correctly, it is like you are not preparing a state in a classical computer and you run something, what is going to happen? Garbage in, garbage out. You initialize state properly like program counter with the start instruction, then you compute, it will produce something. Same thing, your measurement is flawed. So, Rigetti Computing, another company like IBM and all, so they came up with how do we do this eigenvalue solver using kind of quantum processor and classical processor. This one is running machine learning, this has a technical term, it is basically computing ansatz, and this one is basically preparing quantum state. That is where I got the idea that this computation problem can be viewed as a state preparation problem. You prepare the state again and again and again, you measure the term, you compute it. That is actually eigenvalue solving using quantum machine learning. Now, what is state? How do we prepare state, right? So, first question we wanted to answer ourselves when you solve this problem, how people are preparing state today. Even before I became a faculty, quantum computers are there in small scale. So, how are they preparing state? Do you have any idea?
State machines, sir.
No, you prepare the state. If I am angry, what do you want to do with me? Like most of you are not answering my question. If I get angry, what do you want to do? You take me, open that door, put me there, close the door from the outside, and you hope I will eventually cool down. That is what people do. In a very cold, frigid environment, do not do that to me. Very cold, frigid environment, you basically let the qubit cool down. Why did they got excited? They are talking and all that, does not matter. You put them in that frigid environment, and then you kind of know they are prepared to the state. Two problem, you put me in there, and then how do you know when I am going to cool down? If you try open once in a while, if I am so angry I might punch at you. So, there is a risk associated there, but that is also a solution I will come to. This is known as passive reset, you just let it cool down, but only downside is the state preparation problem may not be prepared only to 0 state, because passive reset takes you to the 0 state, and the time it takes depend on how many people around you are excited, how many people are crying around you. That would mean how long you will keep crying or you will be angry. You might be trying to cool down, other people are angry, you should be angry, this is injustice, intolerable. If all the qubits are doing that around you, too many of them, lot of entanglement, then it is going to take a long time to cool down. So, the time is an issue, and also it can only take you to the 0 state, then you have to apply some gate to go to the target state, whatever state you are trying to prepare. What is this state? This is the state that classical machine learning decided what your parameters should be initialized with. Now, then people say, well, this opening the door once in a while to see how I am doing, how angry I am, that is the kind of active reset. You kind of let it cool down, then you measure, and a classical computer kind of checks, yeah, it's cooled down enough, I need to wait few more minutes, like opening door once in a while. What is the problem with active reset? The good part of active reset is you do not wait like indefinitely for this one, you just check. But what is the problem with this one?
You are stimulating it again.
No, you are involving classical computer again. All the speed up you have, first we give up, because classical and state preparation, even within state preparation itself we are involving classical computer again. The slowdown of classical computer is again getting involved. So, what we came up with an idea, I do not think it exists these days. If somebody want to teach their daughter-in-law a lesson, what mother-in-laws do? They beat up their daughter. This used to be the case in 30-40 years ago. So, I thought that is a great idea. Let's if you have 2 qubits, this is the system qubit, I want to initialize, then let us entangle with another qubit, we call it a auxiliary qubit, and let us keep harassing it. Remember the beating it? The harassment is we keep measuring it, and interesting phenomena, actually it all exists in the community, in the physics community, everybody knows about it, anybody in physics. We are the first one to show this will actually work on physical quantum computer, that the simple act of harassment will drive this qubit to the target state. You know the magic, there is no classic analogy. I did not even tell anybody which state I want to go, but it will go to the state. Arbitrary state initialization, we call it arbitrary state initialization using quantum steering. So, in physics domain, developing a theory is powerful, and showing it actually work is equally powerful, maybe more powerful. Remember the topological quantum computer, it existed for eternity, It took hundreds of millions of dollars, maybe more, and 17 years for Microsoft to actually show, and it just happened only few months ago to show it actually works. So, it is not a trivial thing, but either way we came up with this idea of quantum steering, how it would work and what are the limitations, and we kind of worked on extensively on this. Any idea of quantum machine learning, specifically on quantum steering, before I zoom in? Right. So, and basically just to show that you can initialize qubit, these are different IBM quantum computers, but I want to just tell you that there are two ways you can start doing quantum experiments. IBM has a nice tutorial on Qiskit, let me write it out, IBM Qiskit, and you can play with that. It is basically a quantum computer in a simulator environment. If you really want to do real quantum computer up to 5, 7 or very small number of qubits, it is free. You have to create an account in IBM cloud and then you have to submit your job, the quantum circuit. I will show you how circuit looks, how do you prepare, how do you compile, you submit it and then it will process, give you the result. Now, whether actually it ran in the IBM quantum computer or some classical computer ran and send it to you, that also I will talk. How do you know? Yes, please.
Yeah, so you said to check whether it's cool or not, we have to check it. So can we measure the number of qubits which are like acting in weird ways, and then can have a formula to just detect the time how much it will take to cool?
Absolutely, that is how it is done actually. So, every qubit when they are in excited state, they are not in equally excited states. So, you are still measuring, I am only talking about one qubit, but the problem domain you opened up, you are talking about multiple of them. That is a lot more complicated, because everybody will not cool down at the same rate. Some people will stay angry for a long time, somebody becomes very angry, short tempered people very sharp, but then slow down quickly. So, there are a lot of such phenomena. The qubit, even the qubit placement also make a scenario. So, let us say these are the qubit towards the boundary, they will cool down much faster than the qubits that towards the middle, because they are getting they are hot, and other heat or other anger or other whatever excitement, that is also not helping them to cool down. So, that is also true. Now, so active steering, as I said, you open the door and check, and then eventually you might change the unitary how to cool down. So, once you just say cool down, other time you might pat, and whatever it is, it might change active steering. So, we also worked actively on active steering problem. But now I want to show you something more interesting, which actually we saw some result interesting, but or we expected good result and we are not getting good result to publish. And then we sometimes when you do research, you have a hunch we are doing a great work, but your results are not better than the state of the art. Then you kind of see, what did I do wrong? So, for doing that, let me straight take you to the, instead of explaining any of this stuff, let me straight take you to the results. So, here is a hydrogen ground state energy we are computing using passive steering. So, think of in your quantum computer, you build a circuit, you are computing, let us say ground state value, or you are doing eigenvalue computation of an atom. So, you model that atom or that behavior based on qubits. Now, you are measuring, when after the computation is done, the ground value it provided, did it match the mathematical exact one? I think this is, we done this using NumPy solver in Python library, that is what software gives you. Now, then what our problem was, then we are using existing Qiskit. Qiskit has some library to compute it. We are using Qiskit, that blue line, and you see blue line is also there and our work is also right there. So, we are getting the number of exact mathematical computation, so is the state of the art. So, we kind of felt, oh man, all these work went nowhere. Then we observed, we had to zoom in and understand what is this Qiskit algorithm, and it took us kind of time to figure out that Qiskit have an assumption that you have to tell where to start. So, for example, if we want to come to the CET building, our objective is to come to the CET building, but Qiskit is assuming, tell me the front gate of IIT Guwahati, put me in IIT Guwahati front gate, then I can go. So, we did not realize that Qiskit is making that assumption. Now, I know it is silly, you want to prepare a state for somebody and that state preparation says, oh, you need to put me in IIT Guwahati front gate, but that is also a state preparation problem. To do that you have to do something, but it is just that there is a research called Hartree fork, at least for eigenvalue computation. Once you call that function, that is trivial, putting in front of the IIT Guwahati entrance, that is actually easy, but then it needs to travel to kind of or find out the qubit should find a mechanism to travel to the arbitrary state where it needs to reach, right. So, once we remove this and say no, that is unfair, our system is starting with arbitrary state, a random state, you should start also with the random state. If we make Qiskit start on a random state, it is not giving good result. So, then we became happy. So, I know this is not interesting, you are solving a problem and your solution is not right. So, then we have to find out how can you make solution right. Whatever it is, the key idea here is I wanted to explain to you that it may seem lot of things may seem unreal, but that is true in quantum domain, that you can initialize to a known state without even doing quantum computing, but going from there to somewhere that you need to do quantum computing and so on to reach to a state. Now that I am done with the kind of quantum machine learning, I want to take you through little bit, at least let me talk about quantum compilation problem to put everything in perspective. We talked about quantum algorithm, whether it is Grover search, whether the spectral clustering developed by us or source factoring algorithm, you may have some constraints. We use a language called Rust, you can use whatever your favorite language, you can use Python, but the typical synthesis problem there are many, but these two are widely used. If you want the heuristic algorithm, cosine sine decomposition, you want kind of close to optimal, that Solovay-Kitaeb algorithm. Once you do, it is going to produce a quantum circuit. Analogy, you start with a C system C whatever program, and then you get an assembly or you get RTL or get level netlist. Once you have a get level netlist, then we do layout. Oh, actually no, let us do FPGA. So, this should be your let us say this is system C, that analogy will work. System C, this is your RTL or let us say Verilog code, this is your Verilog code, and this would be equivalent to bit streams. If you recall, we are generating bunch of zeros and ones and feeding it to the FPGA, that would be the closest analogy. What is happening? You have the specification of the algorithm, then you have the quantum circuit, then that circuit, now remember we are using the quantum computer through cloud, or you can use directly on the Qiskit simulator, whichever it is, they take exact same input, and those are electrical pulses. I will show you that in a moment, those are electrical pulses. Anybody has a question on this full flow? These are basically, go ahead please. These are basically electrical pulses, the pulses that would be given to the qubit. Yes please.
My question was about electrical pulses.
I will show you the pulses in a moment. Anybody else have any questions? Okay, so basically to generate the pulses, I know I want to initialize a qubit to something. How do I make that happen? So basically the algorithm called grapes are sour, it basically computes that if I start with a random electrical pulse, what happens? Of course, in a simulation model, what happens, and then tries to minimize that cost function. Think of again machine learning, minimize that cost function, and wherever it is minimized, that is the pulse it produces. I am going to show you an exact animation. Before that, I want to introduce a quantum gate called C0 gate. It has a funny behavior, let us not try explaining why it does that. You have two inputs x and y, I put 0 0 0 1 1 0 1 1, and then if x is 1, then y will flip. So, this is y plus x phenomena. So, if x is 1, then it was 0, it will become 1, and here x is 1, this was 1, this will become 0. That is basically the phenomena. If you put in a truth table, this is what it is supposed to be, and as you see quantum gate, if you take a picture, this is what the state situation be, but what it should have happened, this should have been yellow, this should have been yellow. Oh, it is already started, let me go back. So, what needs to happen is these pulses will generate, and when pulses generate, you will see the transformation happens in the qubit. Of course, we are measuring the qubit, knowing what is happening, and eventually if it is working correctly, most of the time it does not, then it should match exactly the expected behavior. Those areas would be have 1 or whatever way you want to look at it, high values, other areas should have low. I just wanted to give a pictorial illustration, and you realize this is also technically incorrect. I am taking a classical analogy, but pulses are exactly electrical pulses. You need to find pulses with certain amplitude and certain duration you need to apply, and you have to keep trying it. The reason we have to try, and remember you Ohm had a question that how do we kind of get to that. If each qubit is actually reliable, then you can mathematically compute and produce the pulses. We have to do all this stuff because qubits are unreliable, and in fact they are so unreliable, every day IBM decides which of the qubits to release. 127 qubit, I do not think they will give it for free, only if you pay, and its payment is like every minute $1000, it is very expensive. If you pay, then they will let you use, even then you will not find 127, 5 or 10 of them will not work. That morning they did not get up on the right side of the bed, and they did not have tea, whatever it is, they are in no mood. So, at the morning the IBM engineers will try to characterize them, we call it characterization. Are they behaving the way they are supposed to behave? If some of them start behaving in a very weird way, then they will be blocked that day for performing any activities. They will not be make available to public. I do not know how they quarantine, what they do, but 127 qubit you might get access to 70 or 80 qubits. Remember 80 qubit is not small, it can compute 2 to the power 80 computation space, that is a lot. So, I am going to skip all of that. If you want to do quantum compilation problem, lot of optimization we kind of published, how do you optimize them, and as you can see every place you have a machine learning using auto encoder in machine learning, you can kind of do that. So, let us have break. After the break we will talk about different solutions including quantum security. Thank you.